Hello everyone, welcome to Gate Pass. In this video I am going to take problems which came in year 2011 and which were related to thermodynamics. So the first problem which I have selected is question number 9. It asks you to find out what is the minimum work W which is required to separate a binary mixture at temperature T0 and pressure P0. Okay, so this is a very similar problem or exactly the same problem which appeared in year 2021. The only difference is that here they have asked you something related to the formula. There they have given you a numerical problem and you have to find out exactly how much work is required. Okay, so let's dive into this problem. So they have given you this relation. First we will simplify this relation. Okay. Now fugacity of pure species I, when it is present as an ideal gas, you know that F pure I, that is equal to pressure P. Okay. So F pure I will be equal to pressure P. So in this case I can replace these fugacities of pure species I by total pressure P, which is nothing but your P0. Okay. Now let's see what is this. This is Fi cap is fugacity of species I in the mixture. Okay, so you have F1 cap and F2 cap. Now if the mixture is behaving as an ideal gas, then the fugacity of species I, they can be given as your partial pressure of that component, and I can write it as Yi into total pressure P0. Okay. So instead of F1 cap, I can write Y1 P0, and instead of F2 cap, I can write Y2 P0. Okay. Now P0 will get cancelled from the numerator and denominator, and now what I am left with is that the total work which is required to separate the binary mixture will be minus RT0 Y1 ln Y1 plus Y2 ln Y2. So what you see is that your option B is correct. Okay. When you see this, what you will observe that the work which is required, that is equal to minus of the or the negative of the Gibbs free energy change of mixing. Okay. And Gibbs free energy change of mixing is given as summation R times T summation over all I Yi ln Yi. Okay, and the negative of this quantity gives you the work which is required to separate a binary mixture. That is the minimum work which is required to separate a binary mixture. Okay, and based on this, a question was asked in year 2021. The next problem which I am going to take is question number 13. In this, the partial molar enthalpies of mixing in joules per mole are given for benzene, which is component 1, and cyclohexane, which is component 2. Okay, so these partial molar enthalpies of mixing, they are given as function of mole fractions. Fine. They have asked you if 1 mole of benzene is mixed with 2 mole of cyclohexane, then what is the enthalpy change of mixing in joules? Okay, so it's a very easy problem. First of all, we will find out what will be x1 and x2. Okay, so your total number of moles is 2 plus 1 3. So your x1 will be equal to 1 by 3 and your x2 will be equal to 2 by 3. Okay, then from summability rule, we know that you have to find the mixture property, that is enthalpy change of mixing from the partial molar enthalpy change of mixing. Okay, so you have to just apply summability rule. So delta H of mixing, that will be equal to x1 delta H1 bar plus x2 delta H2 bar. Okay, so what is x1? That is 1 by 3. Delta H1 is 3600 into x2 square. x2 is 2 by 3. If I do the square, then I will get 4 by 9 plus what is x2? 2 by 3 times delta H2 bar. So that is 3600 multiplied with x1 square, that is 1 by 9. Okay, solve this problem. 3600, I can take it out. Okay, what I get is 4 upon 27 plus 2 upon 27. 27 again I can take out. Okay, then this will be 4 plus 2 6. Okay, then further simplify it. 9 3s are 27, 9 4s are 36, so 400. So this is equal to 800 joules. Okay, but since you are using partial molar quantities, okay, so the whatever you have got over here, this is the molar enthalpy change of mixing. Okay, so this is 800 joules per mole. So what you have calculated is basically your molar enthalpy change of mixing in joules per mole, but they have asked you the answer in joules, so don't forget to multiply it with the number of moles of mixture which you have, because this is a mixture property, so you have to multiply it with how many moles of mixture you have. So you have 1 plus 2, 3 moles of mixture, so multiply it with 3 and then your final answer will be 2400 joules. Okay, this is the step where you may go wrong, because in the options, the 4 options which they have provided, you have both 800 and 2400. If you do not read the problem correctly, then you might in a hurry give this answer, okay, and then your whole question will become wrong. So whenever you are solving a problem, see also what are the units in which they are asking you the answer. Okay, so in this case 2400 joules, it was the correct answer, and that was option B in the given scheme. So the next problem which I am going to take is question number 14. It says that you have 1 mole of methane. It is present in a leak-proof piston cylinder assembly, and the initial pressure is 8 bar and temperature is 1000 Kelvin. Now this gas, it undergoes isothermal expansion to 4 bar under reversible conditions. Okay, methane can be considered as an ideal gas, and you have to find out what is the heat transferred in kilojoules. Okay, so your initial pressure is 8 bars and your final pressure is 4 bars. Okay, you have to assume that this is this process is reversible, and you can also assume that you have an ideal gas. Fine. Now because this is a closed system, I will write down the first law for closed system. And how do I write it? Change in internal energy, that is equal to Q plus W. Since I am assuming that this is an ideal gas and the expansion is isothermal, okay, so you have to further take that this is a isothermal process. So if you have an isothermal process, your temperature is not changing. Since we know that for ideal gas, your internal energy is a function only of temperature, that means your change in internal energy is 0. Then what you get is that Q is equal to minus W. Okay. Since they have also asked you that assume that this is a reversible expansion, in that case the work done can be calculated by integral of minus PdV. Okay, minus will become plus and you will have integral PdV. Okay, now since no information is given about change in V, so I will change the variable from V, integrating variable from V to P. How will I do it? I have PV is equal to RT. Since they have said that this is only 1 mole of methane gas, so I am not writing N explicitly. Okay, then V is equal to RT by P, or if I say dV, that will be equal to minus RT upon P square dP. Okay, so instead of dV, I am going to write over here integral P minus RT upon P square dP. 1 P will cancel, and what you are left with is integral of minus RT dP by P. I can write as d ln of P. Okay, integrate this. So from P1 to P2, what you get is that RT is constant, and after integrating I will have ln of P1 by P2. I am absorbing the negative inside this. Okay, so then do the calculation. What is P1 by P2? Initially you have 8 bar of pressure, finally you have 4 bar of pressure, so P1 by P2 is 2. Okay, put the value of R, which is 8.314, and T, which is given as 1000 Kelvin, so you will get the answer as 5762.8 joules. Okay, so this is the answer which you will get, but Always remember, they have asked you to find Q in kilojoules. So write it as 5.76 kilojoules and see which one is correct. B, option B is correct. Okay. So this was a very simple problem. Okay, and what I will emphasize is that we had also solved problems in which your gas was undergoing adiabatic expansion or compression, and we had to find the work done for that adiabatic process. Here also I have shown you that if it is an isothermal expansion or compression, you need not have to remember all these formulas. Okay, you can start from your first law, and then and there while solving you can reach this formula directly. Okay, so don't try to memorize all these formulas, because otherwise then it makes your thermodynamics very difficult. Thanks for watching my video, and if you like my teaching, please don't forget to subscribe to my channel and hit the like button, and thanks once again for watching. Thank you so much.